Hello, in this example we want to find the rank of A, the row space of A, and the column space of A. So let's begin by putting A in reduced row echelon form. When we do that, we get the following matrix: 1, 0, 7, 0, 1, negative 2, and a 0, 0, 0. From this, we see that there are two pivots or two leading ones. This tells us that the rank of A is 2. This also tells us that the dimension of the row space is 2 and that the dimension of the column space is equal to 2. Okay, so let's go through and find out a little bit more information about the row space and the column space for this matrix. So once we have A in reduced row echelon form, these row vectors, so let me rewrite our reduced row echelon form of A. It looks like 1, 0, 7, and a 0, 1, negative 2, and so forth. These non-zero rows form a basis. So these form a basis for the row space. So we could say basis for the row space looks like 1, 0, 7 and a 0, 1, negative 2. And again, we've got two elements in the basis. The dimension of the row space is 2. And we see that the row space is a dimension 2 subspace of R3. We also see that we have two columns which contain these pivots or leading ones, and so go back and look at what A was. Those columns with the leading ones correspond to the columns of A that would serve as a basis for the column space. So here's one vector, here's another vector. Those correspond to the columns where we obtain those leading ones. And so those two columns form a basis for the column space. So we could say we've got the vector 1, 2, 1 and the vector 2, 5, 1. Again, the column space is a subspace of R3. It's a two-dimensional subspace of R3. Lastly, let's look at a third example. So in this example, we'll call this example 3. Suppose we are given 3 vectors and we want to find a basis for the subspace W spanned by the set of vectors 1, 2, 3, 4, negative 1, negative 1, negative 4, negative 2, and lastly 3, 4, 11, 8. So a couple of things to notice here, just the language of this question. W is equal to the span of these vectors, and if we labeled them U1, U2, and U3, you could say it's the span of these 3 vectors. In other words, it's the set that you get when you do linear combinations of these 3 vectors. And in general, that's kind of a hard problem to work out, because you'd really have to kind of dig in to see what are the kinds of vectors I could generate. But it's much easier to, first of all, figure out what's the dimension of the space W, and second of all, what's a basis for W, and that would fully describe what W looks like. And that's going to be a lot easier than trying to attack this via other means. Okay, so again, lots of ways to look at this, but one way to do this is to say, okay, I'm going to look at these vectors as columns 1, 2, 3, and 4, and a -1, -1, -4, -2, and we'll look at 3, 4, 11, and 8. And if we put this in reduced row echelon form, the matrix that we get out here looks like a 1, 0, 1, a 0, 1, -2, and the bottom two rows are all zeros. Okay, and what this tells us that we've got two leading ones. This tells us that the rank of A, the rank is 2. In other words, we're looking at W being a dimension 2 subspace of R4. It also tells us that we've got some redundancies in here. We've got 3 vectors, but these 3 vectors only span a dimension 2 space. They span some sort of plane that lives in R4. So we don't need to carry around all 3 vectors. All 3 vectors are, in fact, they're not linearly independent. So we only need 2 of them, and the 2 that we need are given by the presence of these leading ones. So those first 2 vectors would be a perfectly fine basis. And there's other sets that would serve as a basis. This is not the only basis out there, but it's certainly one that we can obtain quickly and painlessly with these computations.